Although nuclear energy is widely known for its ability to provide continuous and reliable electricity supply, it also offers significant non-electrical benefits. So our next speaker will talk about exactly that. So Peter Zajac is a professional electrical engineer from ZW Solution. He has many years of working experience in management design, construction, operation, maintenance of electrical power system. He also has working experience in electrical transmission and distribution utilities, which could help us understand better on nuclear energy benefits for remote industrial application. So please join me to welcome Peter Zajac.
Thank you very much. Tony has done my job for me already because he presented so well. So I'll attack the same subject from slightly different angle, from the electrical angle. I'll mention some reactors, but I'll focus on other sources of supply and benefits and pitfalls of using different sources of supply off the grid. Some of the subject will be also related to the big grids, but I'll try to stick to the industrial one. So first, introduction. I was born 745 kilometers from Chernobyl, measured from Google Map, in a straight line under 700 kilometers. I remember very vividly the day when it exploded because they took me to the health precinct and fed me iodine. I still remember the taste of it. Unfortunately, I haven't grown any extra arms, any extra legs, any extra heads. So that organization that was sending the photos of free-eyed fish and reactive koala, I want my money back. Didn't work for me. So, but in all seriousness, I spent a couple years in Papua New Guinea in gold mines, copper mines, silver mines, running power stations. So I have a fair bit of operational experience, and I'll be talking to that. And I'll be talking to the benefits and challenges with renewables and with nuclear and how to overcome those challenges. All right, so industrial and mining sites. They can go from under 10 megawatt, that's a very small, to over 500 megawatt systems. They're less prone to changes between day and night and during the seasons. The loads are typically much more stable. It's a 24/7 operation, and there's no need, so to speak, for base load and peaking. It's a slightly different operation, but it still changes. So the other challenge is in a large interconnected systems, generators are relatively big and individual loads are relatively small. In the industrial systems, a single load can be 10 to 50% of the entire load, which means that if there is a trip, the system has to ride through it. Otherwise, the network goes black. Currently, based on my experience and based on locations, remote sites are typically supplied by a diesel generation or heavy fuel oil engine and turbine generators. That's a majority of them. Those are typically smaller machines in a range of 1 to 10, 20 megawatts. They don't have much inertia, so they're pretty weak, so to speak. The example that's the example of one of the places I've worked. That's a floating power station. It will make more sense in a couple of minutes. But I used to work and I used to operate the floating power station. It was 72 megawatts, 8 heavy fuel oil engine. And heavy fuel oil is a beautiful fuel. It's a marine fuel. It's a leftover from diesel production. And to get rid of byproducts, it has to be incinerated in 1,000 degrees. So it's a fairly dirty fuel. But I can say one thing. I've operated that and I've seen how burning fuels like diesel and heavy fuel oil save lives. I've been there. We've been running hospitals on the island when I've worked for a couple of years, and I've seen those facilities saving lives. And that was the most important thing, that we've been helping people and making people's lives better. and safer for doing that. So challenges are that, again, a trip of one single load can create instability, and a trip restoration of the process takes a couple days sometimes. So, for example, in a larger type gold mine, which uses autoclaves, restoration of power can take 2-3 hours. Restoration of a process to stabilize the process of production takes up to 7 days. So that's a lot of money lost. So again, in mining operation, typically the biggest loads are mills, and they are affected by system frequency. So if the system is unstable, which renewables are well known of, they will trip. That's the thing. The other types of loads, the compressors. If the mines are using underground operations, they have large chilling systems and the winders. Winders on their own can be very interesting because the cycle of winder can be about 2 minutes, and it changes potentially a load profile of the mine by 10% every 120 seconds. Pretty challenging. Okay, so I'll start from showing a bit of renewables in a small off-the-grid system, and I'll show a bit of economy of scale and a bit of costing. It will be somehow related to the large systems, but it will also show that even in small system, large renewable penetration is not that viable. That's easily accessible site in Northern Territory. The load of it is peak 2 megawatts, average daily load 1.5 megawatt. 4.5 megawatt of engine generators, 5 units, so 3 times the average load. Sorry, that's the one. Then it's 4.5 megawatt diesel, 3.9 megawatt solar, and 3 megawatt, 5 megawatt battery. So you see, for supplying of the load, it's 3 times the amount of thermal generation, over 2 times the amount of solar, and over 2 times amount of batteries. So you see the scale of it, the scale and the ratio of the generation to the system. So now let's have a look at in a bit more details about potential cost. And those costs are very high level. They're based on a similar projects that I'm working on. So they're 2025. So if we look at an average supply, average load of 1.5 megawatt, typical capex, solar 1.3 to 1.5 million Australian per megawatt DC, diesel very similar cost per megawatt, BESS similar. So if we look at the totality of it, we talk about $11 million per megawatt. Okay, that gives us about 2 hours on renewables without thermal backup. So the system on a bad day can only run for 2 hours. So let's have a theoretical case now that we have a system 24/7, and we run the cycle of 10 good days, good weather days, and 5 bad weather days. So 1 megawatt system for ease of calculation. I don't want to go too engineering on it. And again, I've excluded all the losses, all the probability, all the statistics. It can get too hard. But 5 days, 1 megawatt, 24 megawatt hours a day, 120 megawatt hours for 5 days. So if we start looking at that we have 10 days of good weather, and we start with a battery discharged, and we have 5 days of bad weather. So on a good day, we assume that the solar can produce 600% of its rating. On a bad day, about 100%. So in order to supply 1 megawatt system, we would need, for 5 days of bad weather, we would need roughly 100 megawatt hours of batteries. 100 megawatt hours. That's about 12, 13, 40 food containers worth of batteries. So the next one, let's look at the price. So for 2 hours, it was costing 11 million to a megawatt of load. So if we look at the solar, we would need 100 megawatt hours to supply the battery and 240 megawatt hours to supply the load. So we need 340 megawatt hours roughly. To do that, we need about 6 megawatt solar farm. So 6 times the size of a load. 6 times. And now let's have a look at the cost, the same numbers. And of course, it's economy of scale. The bigger the battery, the smaller the cost per unit. But for 100 megawatt hours, we still talk more than $15 million to supply a 1 megawatt system for 5 days. Again, there will be naysayers saying, oh, that would be a bit cheaper, that would be more expensive. I've excluded all losses. I've excluded all other costs. That's just a cost. So if we look at it, let's look at the diesel. Let's say that diesel generator 1 megawatt consumes about 250 liters of diesel, confirmed with one of the largest companies running diesel engines in Australia. So 250 liters per hour for 1 megawatt. Large mining companies can buy a diesel for $1 because they buy it offshore, $1 to $1.20 per liter. Not like they don't go to BP or Ample. They don't buy it from the servo. So if we look at it over 20 years, the cost of diesel would be 52 million. So the battery will almost repay itself over 20 years. So when it comes the time to replace the battery, it will almost repay itself, almost. And what if the bad weather lasts for 6 days and not 5? It will go black. Production costs for the mining industry are typically way more expensive than the capex. So someone smarter than me said it. That's not me, but I liked it. Power generation systems run on fuel, not on statistics. That's that. So just to confirm, there are other technical issues, and I don't want to go too far into it, but there are issues with renewables. They don't provide enough reactive power. The Spaniards know very well about it this year. They found out in a pretty bad way. The whole country went black. Spain and Portugal. That's proven that was caused by renewables. They didn't have enough reactive power, didn't have enough inertia. Again, large mining loads require larger amounts of energy to start. That's another issue. Protections may not operate. So they would need something called synchronous condenser. So big synchronous machine to add to renewables, which AMO is talking about installing synchros everywhere now. But that's an extra cost. So with the renewables, the question is for how long? That's a statistical question. And again, it goes to show that long duration on renewables only are not technically or economically viable. For a couple hours, yes. To reduce some fuel use, yes. But to assume that even for small systems like 1 megawatt systems, they can be done forever, no one would spend the money. No industrial application would spend the money to do so. Okay, so majority of mine sites use diesel, they use gas. So the fuel supply chain is a key element there. Because if the fuel is easily accessible, there are roads, there are tanks, there is a storage, that becomes cheap, then gas engines, gas turbines, diesel engines become cheaper to operate. But what if the supply chain becomes a problem? The more and more mining is being required in a more and more remote areas. As I said, I used to work in Papua New Guinea on a little island. So the only way to bring the fuel was shipping. So let's presume there is a new mine in an offshore location, and it needs gas because gas is cheap, gas is reliable. But if there is no supply chain contract signed there, they'll have to build a port, they'll have to build a storage, they'll have to buy the ship to bring the fuel. And then the ship and the port have to match. It's not that they will send a massive ship, because if the area around the location is not good enough for the ships, they have to create something, build something, buy something. That's an extra cost. That's where nuclear starts playing key role in those more remote locations. So example of study done: liquid gas storage, floating. To store gas for 100 megawatt plants for about 2 weeks, it costs hundreds of millions of dollars just for 2 weeks. And the ship would have to turn every 2 weeks. Plus, LNG can be only stored for certain periods of time before it has to be flared and mixed and stuff. Otherwise, it can't be stored forever. So that's another problem. Then one of the key elements for mining is very land intense, especially open cut mining. The mining pits are huge. So why nuclear? Let's look at it. We have a wind farm, we have a solar farm, and the little blip there is like 10 times. That's the real comparison. So if someone wants to explore and mine around, the less land used for anything else than mining operation, the better for the operation. It's not only that it's efficient, etc., but also if there is an ore under the surface, people will want to mine it. That's the goal. That's the goal of mining, to get the dirt out and recover the ore. So the less space is used for any other services, the better for the mine. The longer the mine life, the cheaper the operation across the mine life cycle. Why else? Why nuclear? In here, the nuclear is in top 3 of the safest, but that excludes the Texas and Iberia blackouts, which would shift the number of deaths per terawatt hour, and etc. From another source, nuclear is the winner, the clear winner in terms of safety. Again, long life cycles in remote areas is a benefit. The big mines can last 40, 60 years. If there's enough ore for 40, 60 years of exploring, the mines can be pulled. So also nuclear is immune to man-made damages, dust, tremors, etc. Nuclear can co-generate steam. In lots of mining and processing areas, steam is required, so it's okay. Okay, but, and sorry, Tony preambled that it does exist, but I try to be surprising. I failed miserably. But someone will say, oh, only 30 to 50 meg reactors. The small ones don't exist, only the big ones. Okay. That's why I was showing the floating power station. That's the floating nuclear power station right there. It's in Russian town of Pevek, which is an industrial town. It includes 2 generation 3 plus pressurized light water reactors, 35 megawatt electrical each. It was operating for, I believe, 5 years now. It was either energized in 2021 or 2022. And one of the loads that it will be supplying soon is a gold mine operation. So it supplies the town, it supplies the port, and it also will be supplying the mine soon. Some parameters of it. So as Tony has said, it uses the enrichment of 20%, so still within lieu. Some more details. I got the price from the Russian website, translated to English, and it costed about $460 million US. So it includes also quotas for 70 crew members, etc., etc. So if that was stripped, those portions, it's actually cheaper per megawatt than renewables for that scale. So again, there will be people saying, there's some history of it. There will be people saying, "Oh, but it takes so many years to build a nuclear reactor. It takes 7 to 15 years to build a mine." So if the processes start in parallel, it's not a problem. Mines are not being built in 2 years. The exploration process, then the amounts of materials to bring to the remote locations, it takes years. So time is not a problem. There's another series of other reactors, and actually RATM 200, I've almost worked on one, because the mine that I used to work, they were considering buying one of the Russian icebreakers, but then Fukushima happened and that stopped. But they were already visiting Russia to observe one of those machines. So bad luck on me. And they still use the fuel enrichment below 20%, which Tony described much better than I did. So the challenges. Nuclear can be mixed with different types of storages. So for example, if the mining uses oxygen is required for autoclaves, etc. Oxygen can be stored. So the balance between a peak load and a smaller load can be balanced. The other thing is lots of hard metal mines use tiling dams. So they pump water, they use it for processing, they send it back, it settles. Okay, two things, 20 seconds more. So it can be used with batteries, it can be used with pumped hydro, which can be built as a part of a processing facilities. So nuclear can be very, very flexible and beneficial. If anyone wants more data on the icebreaker, that's it. And those are my contact details. Thank you very much.